Thank you, Constantine. Yeah, a couple years ago, our group in Chicago, we're based in Chicago, was approached by Samsung to do a design for a new headquarters building in Beijing. So this was going to be a 60-story tower, 59-story tower, 260 meters tall. And although wind was an issue, obviously, if any of you have done some work in Beijing, you know it's a high seismic zone. One of the requests by the client, Samsung, was for us to actually investigate the use of newer technology. We're using a basic system that's used with a lot of tall building designs. It was a reinforced concrete core linked to composite columns through an Outrigger system. But at that time, Samsung wanted to have an idea about if we were to implement some newer technology into the system, could we get a benefit from performance? So in response to that, this is the case study that we did. We looked at a conventional Outrigger system, and we looked at actually utilizing either conventional steel for the Outriggers themselves, or also using a BRB brace or a pure viscous damper. And Taylor Devices helped us with that study. The advantages of an Outrigger system are obvious. It's an efficient way to increase the stiffness of a building by linking the perimeter columns. So you're bracing the core by linking it with the outside columns. It's also minimum architectural disruption. So you find the level, usually mechanical levels, where you're actually going to implement these braces, and it's a good way to get around actually increasing stiffness and with limited architectural impact. Disadvantages that you might have are there's large localized forces that are created when you're linking a core wall to outside columns. Thicker walls and embedments, embedded steel are often needed because what happens with the Outrigger system is you create large panel zone shears as you're transferring load out to the outside columns. Damping could be in the form of pure viscous damping or hysteretic yielding. So the fluid viscous damper system that we were using was a pure viscous damping system. We also looked at buckling restraint braces, which they're hysteretic yielding beyond the elastic limit. And then damping elements do not resist static load. So that was a key point between the BRB and conventional steel brace system versus the viscous damper system. With increased stiffness, you also increase the seismic loads, so that was a concern of ours. And that's what we wanted this comparative study to show us, how much actual additional good behavior could we get out of using the viscous damper as opposed to stiffening up the building using conventional systems. And increasing damping results in decreased seismic forces, but it's also less stiffness. So there's a balancing act. At some point, the viscous damper is actually not beneficial. For a prototype building, 260-meter tall tower, 59 stories in Beijing, concrete shear walls, composite columns, steel perimeter frame, and 3 options were considered. The conventional steel braces had a yield force of about 67,000 kilonewtons, so they were large diagonal members. The buckling restraint braces had a yield force of about 5,000 kilonewtons. And this is a brace size that has been utilized on some work out in the West Coast. Actually, some work that MKA did on a building out in San Francisco, so it's comparable to the size of the BRB braces they're using out there. The fluid viscous dampers were a rated force of 5,000 kilonewtons, and Taylor Devices was helping with, they actually did a lot of work to help us out with the conceptual design of those units. BRB brace, if you haven't utilized one of these before, it's a steel core with a debonding on a zone, and a steel tube is actually encased around it. And what happens is you actually get the element. The idea of the steel jacket is to yield the element in compression, so it's behaving and it's dissipating energy the same way it would as a pure tension element. Viscous damper is different in that it's an assembly on the end of a steel brace, and it's a pure viscous system where a fluid is encased in that, in this manifold here, and then energy is dissipated that way. The prototype building for a comparative study, it was Outrigger systems were implemented at about third points up the building, so about every 20 stories. On the BRB and the conventional steel brace system, we also utilized a belt truss. And the idea was that we were trying to get a good linkage with all the columns around the perimeter. We actually did look at this utilizing the viscous dampers in the diagonals, but if you've ever done a study on the outrigger systems, this can behave as an outrigger without even the diagonals actually in the zone, because you're transferring shear in and out of the page through a belt truss if the belt truss is stiff enough. So we actually found we had better behavior in the system by taking the belt truss out just for the viscous damper system. So all the other elements, this was just a comparative study. We weren't actually looking at the cost effectiveness of taking down and minimizing every element in the building for each different scheme. So in this case, we ran a base scheme that had all the same composite column shear wall sizes, just to see what the additional benefit of using different elements was. And in this case, you know, the viscous, the only difference in the steel tonnage was really due to this level, these levels at mechanical levels. The outriggers were actually implemented in each of the setback levels, so it was a pretty significant core for the bottom 25 floors. The second, third, the core stepped back asymmetrically, and in the upper zone it stepped back again. BRBs versus conventional braces, it's just a concept hysteresis loop, showing that with a conventional steel brace you lose the ability to dissipate energy once the element buckles in the compression zone. Conventional steel outrigger is a stiffness element, so it resists displacement. Fluid viscous damper, it actually, its force level is related to a damping coefficient and also a damping exponent value on the velocity. So it's always resisting motion, and that's a fundamental difference. And then with the design of a damper, you are actually setting these values, the alpha value that can vary between 0.3 to 1. And 0.3 is more of an element that would be engaged for frequent level earthquake levels and also design wind levels. And 1 is an element actually where it behaves more rigidly, almost like a steel brace. Fluid viscous damper force is 90 degrees out of phase with a normal outrigger. So it's always opposing the building's direction of motion, but it's a key advantage when resisting dynamic loads because it allows the fluid viscous damper outrigger to effectively resist building movements with a lower force. And so these plots kind of show you that idea. Obviously you have more damping, so the motion is damped out, it's minimized. But when you look at kind of a fundamental difference here is with the outrigger system, when you've actually reached your a minimum, the viscous damper is already up at its highest level, and the viscous damper force is down at a 0 point when the outrigger has reached a maximum. And just some diagrammatic ideas about with a conventional stiffness element, you're actually resisting forces only when you're actually getting displacement in the system. And a viscous damper system would always be resisting that force because it's just looking at motion. One approach with dampers is to utilize them in a distributed way. So a large number of dampers are incorporated into a brace frames. There's more uniform damping throughout. And so when you're looking at an earthquake, higher modes of effect are actually occurring. So having a more uniform distribution may be a benefit. A simplified analysis for doing design in these conditions is actually included in ASC 7, Chapter 18. An example of a building, and this old Cantor Cynic building is the Torre Mayor building in Mexico City. It was a 225-meter tower that was completed in 2003. And so this just gives you a shot, and this is a high seismic zone. An alternate approach, and the approach that we chose to actually look at in this case was for outriggers only having dampers at specific locations. So relatively few dampers. The distributed case here had about 60 dampers in the brace frame system. But in this case, we were looking at only isolated locations, so about 16 damper locations. Potentially, it would be more cost-effective, but it depends on the system if it actually is more cost-effective, so that's why we wanted to study this. An example of a building that has implemented a strategy like this is the 250 West 55th Street. So this is a recently completed building by Arup, I believe, and it's 185 meters tall. So a picture of that building. And these dampers, there's dampers up at the top of this building. When you do the design, you actually can affect the values, so the damping coefficient and the damping exponent value. So you can look at a range of different designs where you vary those values. And in our case, we were looking for a system that would actually, in the beginning, we thought that we might design a fused damper system, a system where it kind of was engaged as a stiffness element for the lower level earthquakes and also design wind loads. But in our case, we got so much benefit out of the lower level loads that we actually were looking at utilizing it even for those loads. There are some useful ways. There are some design methods that are out there for conventional design by ASCE. And so we did look at that as just kind of a helpful way to gauge whether or not we are on the right track and to check our nonlinear analysis. But in the end, there is no way to design other than just doing a full nonlinear time history analysis. These elements are nonlinear. So, in looking at damping, these were the force levels that were developed for the different earthquake levels and surface wind. You can see the wind levels, the forces were quite a bit smaller, even than frequent earthquake. And these were all Chinese code frequent, moderate, and rare level earthquakes for that zone in Beijing. What we did was we tried to get an estimate just so that we could gauge how much damping we were getting just due to the supplemental damper. So we did run some nonlinear time. We had nonlinear time history results, and what we were trying to do is try to gauge those by setting up time history records and analyzing it to try to match up with that, just to get a gauge on how much supplemental damping we thought we were getting out of the damper itself. One of the concerns that we had was with wind events, because the movements were quite a bit smaller. Taylor Devices has actually done some modeling, and I think they did it specifically some testing work that they did for their New York project. Initially, you can estimate what the damping is by doing a damped free vibration study on the tower with the dampers in the model, in the nonlinear model. So in this case, we initially were looking at the full displacement of the units, but in the end, we actually just did a full displacement for the dynamic effect. And so we got help from the wind tunnel to figure out how to do that. There is some effective damping that is reduced due to friction forces under very small displacement, so there is a little bit of a loss of efficiency. The results, the dampers contribute about 4.5% supplemental damping at the 50-year wind. So there's quite a bit of additional supplemental damping. And based on 4.5 supplemental damping, 50-year wind overturning moment reduced by about almost 40%, and the 10-year maximum acceleration is almost by 50%. So this was the primary reason why we decided to recommend not using a fused device. We wanted to have something that was engaged even for the design wind levels and the frequent level earthquake. The idea is there are conventional ways to look at supplemental damping by ASCE and to estimate a design. And so we did that, but just really as a sanity check to check what we were doing with our comparative study. So you can look at a response spectrum with fundamental building periods and estimated global damping ratios to try to figure out, like with different options, what kind of response you should get. And this is just a chart from ASCE 7 that shows how supplemental damping values are chosen. Gives you an indication of what we set for those parameters. And this was really just a sanity check. But one of the interesting things out of this is we had an idea that even when we were looking at the nonlinear analysis, that we should get results where the fluid viscous damper, it turned out, implemented into the system, got very good response on the force levels that we would see at rare, moderate, and frequent. But comparatively, at rare displacements, the values were actually worse than the conventional system. So that's what we were looking for in the time history analysis, the nonlinear analysis. We did nonlinear analysis models using Perform 3D for each of the three options. 7 orthogonal pairs of ground motion time history, so all the usual stuff. Material nonlinearity, obviously the outrigger levels and the dampers themselves, concrete walls, perimeter columns, perimeter beams. Belt trusses were conventional outrigger and BRB only, so we didn't have belt trusses in the damper scheme. P delta and then 2% inherent damping. And the interesting thing to look at this slide is the blue being beneficial response and green being kind of in the middle. What you can see is in the final scheme, the fluid viscous damper had better performance in every category going down the line, except in the rare level interstory drift, which is what we would have expected just based on using like some rudimentary design checks by ASCE. The other key thing about the study that we wanted to highlight with the client also was that energy dissipated by other structural elements was significantly more with the conventional system than the BRB or fluid viscous damper system. So in a qualitative sense, you can look at these numbers and equate those to increase the level of increased damage you might have in the system for those different moderate or rare earthquakes. And this just shows that there was a benefit even at the frequent level for the earthquake. This is hysteresis loops on the fluid viscous damper, and you can see the BRB was engaged a bit at even the frequent level and moderate level, the hysteresis loops. And the amount of energy you dissipate is really related to the amount of area underneath within each of these loops. And then this at the rare level. So by the rare level, the BRB was pretty well developed too. And then some of these plots, and I think these come right out of Perform 3D, they're really useful to kind of qualitatively think about the system. This is a conventional outrigger steel system. You can see more energy for the whole system has to be dissipated. And there's a certain percentage that is just inherent damping that's consistent across the board. But then also the structural system has to have some yielding or some damage to actually take into account or actually dissipate that energy. This is at the scheme for the BRB. So now you see the BRB engaged in some dampening out effect or some energy dissipation. And then finally, the total force level has gone down because the response of this building, it has a longer period, so just less energy has to be dissipated for a rare level. But then also there's a significant portion of the load that's actually dissipated in the damper itself. So conclusions, the spectral estimates were effective for predicting trends, not exact numbers, but trends that we use as a sanity check really for the nonlinear time history analysis that we were doing. The fluid viscous damper scheme generally performed the best, experienced the lowest forces, dissipated the most energy, minimized structural damage, and it had the smallest drifts for frequent and moderate earthquake. The conventional steel brace system actually didn't perform as well. It experienced the highest forces, and so we had our panel zone design issues still. Dissipated the least energy proportional to yield and greatest structural damage. However, it did have the smallest drift under rare earthquake. So you couldn't say an across the board performance was better for the viscous damper. It depended on what the issue was. And the BRB Outrigger's performance was in between the other two options. It dissipated energy. It was significant under rare level earthquake, a little bit under moderate level earthquake, and none under frequent. So it wasn't really engaged for a frequent level earthquake. It was the second best for minimizing structural damage, and the size chosen, the 5,000 kilonewton capacity, minimized localized forces at the panel zones, but it was also significantly less effective with no extra damping, significantly less stiffness with no extra damping. It hurt its results at the frequent level. Maximum benefit, and concluding, maximum benefit can be achieved by increasing damping in lieu of stiffness for dynamic loads. And here I would say sometimes. I mean, in our situation, we had quite a large core, and there was a situation where, like, even at the rare level earthquakes, the amount of additional supplemental damping we got offset the fact that we were losing stiffness. The damping elements are always in motion, except when they get to a maximum deflection point, so allowing movements to be controlled with smaller forces. And this allows the building to meet performance objectives with lower stiffness. Less structure needed to provide required stiffness, the lower forces under seismic loads, and less structure needed to provide required strength. So, and that is it. Thank you.